First that we want to discuss is, let's talk a little bit about how do we actually build a cloud service that communicates with devices. So quickly just kind of showing you a diagram, this is essentially what you just saw in the demo, right? The user can interact with an assistant-enabled device, and that assistant device will interact with your cloud service in order to communicate with that particular device. So the smart home interaction is a cloud-to-cloud integration. Okay? Which means, as a device manufacturer, you have to provide your own cloud service for users to register and manage their devices, and then the Smart Home Actions platform can integrate with that cloud service using a series of webhooks to control and access those devices. We'll talk more about that in a little bit. Now, depending on where you are in your development process, you may already have this functionality in place for your devices. But I want to explore a little bit of what an example might look like if you were to build this device cloud service on Google Cloud. So this is an example architecture using services from the Google Cloud Platform, as well as from Firebase, that we use to fulfill the requirements for the smart home use case. Now, the sample code for what I'm going to show you is on GitHub, so I recommend that you take a look at that after the talk. It's an end-to-end sample that includes the cloud service, as well as client applications for mobile and web, interactions with sample devices, all of that stuff. So in this sample architecture, we have Cloud IoT Core, which enables secure device connectivity over MQTT or HTTP. We're also using Firebase, which enables easy client application development for mobile and web through their series of native SDKs. We also get access to Firebase authentication, which adds the ability to provide user identity and access control over all of this data. Now, in this example, devices report their current state through IoT Core, which then bridges that data into PubSub and through to Cloud Firestore. Using Firebase authentication and Firestore, we can build client applications that expose that data directly to users for device management. And then users now have the ability to control their devices, and they do that by updating the data in Firestore, which then triggers commands back to the devices through IoT Core. Now, this means that in this architecture, Firestore becomes the primary source of truth for all of your device data. And that's going to become really important when we start talking more about smart home. So I'll come back to that a little bit later on. But just keep in mind for now that Cloud Firestore is that central point where all of the data is accessible for all of the devices. Okay, so why Cloud IoT Core? IoT Core enables secure connections to Google Cloud for resource-constrained devices. Okay, think small, tiny, $1 microcontroller, less than $1 type devices, right? Generally speaking, if you're building something like a smart light, you're not going to want to put a quad-core processor in there running embedded Linux. I hope. Instead, you typically want low-power devices that have very low footprint and all of those things. So we use Cloud IoT Core to enable those devices to connect directly to Google Cloud, and that's done two ways. The first is using MQTT, which is a low overhead protocol that is ideally suited for IoT devices or low bandwidth devices. Okay? We do also support HTTP, but generally speaking, most users of IoT Core are using the MQTT protocol, primarily for this reason. The other and probably more important reason is for authentication. So we need to make sure that these devices have a secure connection to Google Cloud. And as I mentioned before, generally speaking, we try to get the smallest, lowest footprint, cheapest device we can into these smart home devices, whatever we need to supply the use case. This often introduces constraints on both CPU as well as memory, primarily memory, right? The cheaper the device, the less onboard memory it's going to have. In addition to this, IoT solutions really to be secure need a mutual authentication solution. Okay? It's not enough for the device to be able to trust the server that it's connecting to. It's just as important for the server to be able to trust the devices that are connecting to it in an IoT situation. Okay? So we need to have mutual authentication going between these two pieces. Generally speaking, you would solve that problem with something like a mutual TLS stack on your device or on your client. However, typical mutual TLS stacks require way too much memory for a microcontroller. in a lot of cases. Whether it's the stack itself or the fact that the client is also responsible for housing the full certificate chain that it has to supply up to the server, all of that stuff can blow out the memory of a microcontroller very, very quickly. So Cloud IoT Core is designed to solve this problem by creating an asymmetric authentication between the two. It still uses TLS 1.2 to authenticate the server to the devices. So IoT Core still presents certificates that can be validated on the device and all of that stuff. But the devices authenticate themselves back to IoT Core using a much simpler public-private key authentication mechanism using JSON Web Tokens or JWTs. Okay. Basically what happens here is when an IoT Core device is connecting to the service, it signs a JWT with a private key that is stored privately and securely on that device, and then provides that JWT as the password for the connection to IoT Core over MQTT or HTTP. The public key is shared at provisioning time with IoT Core. So it can use that public key to validate that the information coming in from this device is valid, it is the device ID that it's claiming to be, and all of those things. So we still have a secure authentication mechanism from the client device back up to the server, but it's using a much more lightweight process that is more easy to fit into these constrained embedded devices than a full-blown mutual TLS. All right. One of the advantages of using Firebase authentication for user identity and access control is security rules. Has anyone developed using Firebase in here? Okay, just a few people. Firebase is an amazing platform. It is built on Google Cloud, but it adds a bunch of additional developer services that make it really, really integrated, seamless, and easy to use. And one of those is Firebase authentication integration with data store using the security rules. So with security rules, we can seamlessly integrate user permissions to access the Firestore data using a very simple declarative rule syntax without having to write any code. Right? And this syntax allows us to validate, based on the authenticated users and the information that we have about them, what types of data in the database should they be able to access. Right? And this is basically a snapshot of the Firestore rules from the end-to-end example that we have, which allow us to control that only authenticated users should be able to access device data, and they should only be able to access the devices where we have marked them as the owner of that device. Okay. Now, the logistics of how all that happens is you can look in the sample code, but the basic idea is with just a couple lines in the rules, we apply that over our entire database. Okay, so it's very simple, it's very seamless, it's easy to do. We can also restrict not only user access, but users' ability to do things like create new devices, right? So that we can mediate the process of device registration, and we'll talk about that a little bit more in a minute. Okay. Along with security rules, one of the other primary advantages of Firebase is the ability to build client apps, as I mentioned before. So this is a screenshot of the mobile app that comes along with the end-to-end example. This happens to have been written in Flutter using the native Flutter SDK that's available for Firebase. Firebase also has SDKs for Android and iOS, and on the web we have SDKs for React, Angular, and many, many more. Right? So it's a very easy system to integrate for front-end applications, both on the web and on mobile. Okay? And this enables you to very quickly create properly functional applications to enable users to authenticate, access their devices, manage them, control, all of those types of things. Now, the mobile application in particular is actually quite important because it's part of a critical path for device provisioning. It allows users to activate and register their devices. So I won't ask for a show of hands this time, but I'll bet that those of you who mentioned that you have activated a smart device in your home before, more than likely you had to download the mobile app from that manufacturer to provision that device, whether it was on your network or with your account or any of that. This is a very common pattern because it's a device that we can pretty much assume that all users will have with them. Right? Some devices can do this on the web, most of them use the mobile app. So let's dive a bit deeper into the device provisioning process and how we might do this with something like Cloud IoT Core. So within IoT Core, I mentioned before that devices use this public-private key authentication mechanism when they connect to the service. So one of the things that the OEM or the factory is responsible for doing is producing that key pair and ensuring that the public key is shared with IoT Core and the private key is securely stored on that device before it's boxed up and ready to ship. That basically creates the initial device association to say that this is a valid device, this is its ID or serial number or whatever you want to provide. That can be done by the manufacturer. But then at some point later, when the user actually takes this thing out of the box, we have to have a way for them to prove that the device they have in front of them that they're trying to register is a valid device that we know about. Okay? One of the ways that you can do that is you can share that same public key with the user so that they can provide that public key during device registration and allow us on the back end to validate that the public key matches the one that's in IoT Core for that particular device ID. Okay? And there's a number of ways you could do that in terms of how that information is shared. One example, which is how we do it in the example code that I mentioned to you earlier, is you can bind that public key to something physical on the device, like a QR code. And this is a very common provisioning method that's used by a lot of smart home vendors. One of the nice features of this functionality is that it actually enhances the security of the device as well over doing provisioning methods wirelessly like BLE or MDNS or some of those others. Not that there's anything wrong with those, but they require additional layers of security to make sure you can prove that that device is the one you're talking to. Right? When you physically bind this data to the device, you can guarantee that the user has to have physical access to the device in order to register it. Okay? So you can bind all of that data. Maybe you want some additional metadata like the device serial number or anything else, but the public key in this example is the one that's most important. You can encode all of that onto the device using something like a QR code. And then, because all of our mobile devices have cameras, you can use the mobile application to scan that QR code, gather that information easily, not asking the user to type it in or anything like that. They just scan the QR code, submit that device information up to Firestore, and then our backend service can then validate that information. So the user basically submits a request to register this device with a particular device ID and public key. And then in the backend, we can validate with IoT Core, oh yes, that device ID does exist, here's its public key, and that actually matches what the user has just given you. Okay, so we know to a reasonable degree of certainty that the user actually has the device in front of them that they're trying to register. Okay? And then from there, we can create the actual device node, assign that user ID as the owner, and then the user can see it in their mobile app, on the web, and all of that. Okay, so that's kind of a quick overview of the example code. I encourage.
So let's jump into Quick Labs. You can check out the link to start the Quick Lab here. You'll need to set aside about 40 minutes to complete it.
This hands-on lab will show you how to use Google Cloud Platform Console to create a Cloud IoT Core device registry, connect a device, and publish device telemetry events. So far in the lab, we've created a device registry with a Cloud Pub subtopic for publishing device telemetry events. We then added a device to the registry and added a public key to the device so that it can connect to GCP. We did some setup to run a Node.js sample to connect a virtual device and view telemetry. Once at this stage, we'll run this command in Cloud Shell to create a subscription to the registry's pub subtopic. Then we run this command to connect a virtual device to Cloud IoT Core using the MQTT bridge. The output shows that the sample device is publishing messages to the telemetry topic. 25 messages are published. Finally, we run this command to read the messages published to the telemetry topic. We created a Cloud IoT Core device registry, connected a device, and published device telemetry events.